Hi, this is Giovanni da Prat speaking, and welcome to example 12. In case you have any questions regarding the content of this material here, or you want to discuss or have some doubts, please feel free to contact me anytime. Okay, example 12 deals with an unconventional gas reservoir, and in this case we're going to uh, present a rate transient analysis instead of pressure transient analysis methodology, which is applicable uh, commonly to unconventional, in this case, shale gas reservoir. Here is the data, reservoir and well data, and this is the horizontal well configuration with fractures normally for, in these cases, quite low permeability. We need to get production. The only way is to get fracture in the well and multiple fractures. And that's because the low permeability that characterize the shales. So even though we may do some pressure transient analysis, it is quite uncommon to reach radial flow and other flow regimes. Instead, we're having linear flow, bilinear flow related uh, to the fracture and the communication to the fracture to the reservoir. So here is what we're going to present, the analysis of both rate and pressures. These are bottom hole pressures, these are rates and the cumulative. And this is just a history for 3.32 years of a well. And we're going to analyze the data and explain how is rate transient analysis done. Before that, I would like to introduce some basic concepts in case you're not familiar with rate transient analysis. And basically, it become popular for unconventional reservoirs. Rate transient analysis has a long way already established in the industry. But in the case of unconventional reservoirs, it is mostly used rather than pressure transient analysis. So the situation is that constant bottom hole pressure, except in that case, we know that the rate and the bottom hole pressure are variable with over time. It could be true for conventional reservoirs too. So we're going to use the rate normalized pressure in that case and the pressure normalized rate. So and the main diagnostic plots are the blasting gain plot that we will explain soon, and the rate normalized pressure. The blasting gain plot is a plot where you can see here, it's the definition is a normalized rate that you can see here, the one over here. Let's show me better. Oops. Um, and the integral of the normalized rate, that is here, and finally the integral of the normalized rate derivative, which is this one here. So the normalized pressure derivative, its integral is shown here. You see here there is a scattering noisily data because we're using the equivalent time, which is defined like a cumulative over the rate at some time t. When we use pressures and we use time, you know the pressure is acquired with a frequency, let's say seconds if you want. But here is when you enter with the flow rates, you know that unless you have a spinner continually monitoring the rates, you have to deal with the daily productions, and in that case is better. It is suggested to use this equivalent time. So you have your normalized pressure here versus this equivalent time, And one a help here is if you do the integral, then you can see here that you get a better, this data is not as scattering or noisy, let's say, than this one here. So the definitions are here, just the integral is just like that, the integral of this um, changing pressure and rate, and the derivative defined like this. So in practice, rate transient analysis carry out considering the entire history of production and pressure and achieving the simulation of flow rates and pressure data values using analytical or numerical models. Here is an example. You have here your production and you have also your bottom hole pressures. In many cases, these bottom hole pressures are you can get them from the surface wellhead pressures. Then you can do that. And what you see here is the reservoir pressure, bottom hole pressure, and a match, which you get the match using models. And once a good simulation has been achieved, a good match, the results can be used to calculate the expected value of future flow, assuming values for bottom hole pressure. In this case, we're trying to, let's say, compete, if you want, with the classical decline curve analysis. That is an idea also that we will see later, how to get a forecast on the rates. So what you do, you got here, you get your model by simulation, simulating all this data and rates and pressure, and then from here on you can make let's say a forecast, and then you just use a constant, or you can use a ramp or pressure, or you can decide it on which do you think the pressure is gonna be based on this or in the operational side. So once done this, you can do this forecast here. And this is a very basic just presentation of rate transient analysis. As I said, has been in place for many years, like pressure transient analysis. But in this case, as mentioned before, for unconventional, it's going to be of great use. So let's go back now to our data, production, bottom hole pressure, and cumulative here. So depending on fracture system configuration, simple or complex solution could be either analytical or numerical or both. According to microseismic here, is not you know that you can get an idea on the configuration of your fractures. In this case, we're having this, as I previously shown. This is a simple configuration, but you may have a configuration like this. According to the microseismic dawn, you can see that this is rotated fractures. This is all depends on the stress when you start doing the fracture. You have to deal also with the stress. And in this case, you can use analytical and numerical, similar to this, but what we see here is a little bit different. It's a configuration quite, you have not only, you have rotation, and also you may have a situation like this. Okay, so what we did with the data previously, and I'm gonna show you that with the software later. You do your rate normalized pressure, you identify the model, this is linear flow, and eventually what you see here is a bending or in the derivative, meaning that the fractures are interfering each other, and therefore you try to go to the to like eventually like reaching a pseudo steady state in the stimulated rock volume. And this is your blasting game plot. So we got already a good match here. So what we can do is to extrapolate, assuming values for the bottom hole pressure. Or before I show you this. This is, I would like to also to mention you that this linear flow plot, which is just the pressure, normalized pressure versus the square root of time, which in conventional reservoirs also, you can get from here your your fracture half length from the linear part. And this nowadays is very popular to use to monitor if the fracture is becoming damaged with time, with production time. As you know, in a conventional reservoir, there is a situation with the stress dependence, and therefore the fracture itself with time could be subject to a big stress and therefore lose its properties or the conductivity properties. So this is quite used for monitoring. Okay, here what we said previously, once you have a good have simulated your data, you can go ahead and let's say make a forecast for 30 years production, and you can even say you can get here what is your value at the end of these 30 years. So this is what we did with the simulator numerical. So this is 709 2013, and then you can go until 2046 because of the 30 years production, and you get here your pressure profiles um, around the inside the system, and also you can see here that there is some contributions from the unconventional reservoir not fractured. Still, you can see here the pressure is also almost the initial pressure. And uh, this is what is done normally uh, to uh, to to have a forecast, let's say, of the system. Okay, now we're going to enter to decline curve analysis methods, which are commonly applied for unconventional reservoirs. The power loss potential, the equation is defined here for the flow rate. The stretch exponential here. The ARPS, which has been used since 1946, not for conventional reservoir actually. And as I remember, when this unconventional reservoir started playing a role, initially many of the decline curve analysis were using ARPS. The situation was at that moment, or still, that the coefficient was, for many cases, was bigger than 1. So it has been some controversies here. So another method you can use is Duong, and this is from Kappa software, and the logistic grow also. All these methods has constants here, declining constants, that you can get once you do the match. I'll show you later. So the ARPS hyperbolic results are here for our example. We made it here, we did a match, and you can get here the information. In this case, the B value is, the constant B is 0.97, still is not bigger than 1. And your expected ultimate recovery is 3.6. billion standard cubic feet. So we did this with the different methods, and as you can see here, this is a power loss potential. You may have a fit compared to the previous one. There is no a good fit here, and you got 2.56 billion standard cubic feet. This is the stretch exponential also. You can see a reasonable fit though, but compared to ARP's hyperbolic is not as good. So here you have the parameters that characterize that method, and here is the value for the EUR. We go now with bone results. You can see here also a match, a reasonable match. And in this case, as I think was mentioned in the literature, this method gives you quite a big estimate compared to the other methods for the EUR. This is the logistic growth. You can see here there is not a good match. And you got this low value. You can see here from the forecast of the tendency for the EUR. And this is the one that use kappa. Again, you can see there is not quite a good match. This is the value that you have for the EUR. And so rather than conclusion, I will make some comments here. And due to the inherently low permeability that characterizes shales, pressure transient analysis methods are applied mostly to the linear or bilinear flow regime associated to the presence of the hydraulic fracture system. Actually, the well and the hydraulic fracture system is your reservoir, let's say, for most practical uh, situation. You know, once you define your reservoir, which is the fractures, the length, the half length of the fractures, and the length of the well, then you have kind of a elongated box, let's say, and here your reserves, you can get an idea of the volume contained, and you won't have any, at least you have an idea of how much can you get from there. So repeating here, because bottom hole pressure and rates are declining, then it is this method it is more appropriate to use. As we seen saw before, different DCI models applicable to unconventional reservoirs have been applied, and some of them match the data better than others. And for this particular set of data, the ARP's hyperbolic method seems to be a good choice. This is just for the data we got. Now, if you think about extrapolation, then it's another matter here. So it's better, or not better, but it's good to compare with what we did before using the rate transient analysis, using both pressure and rates, because this is rather and compared to the decline curve method. So in this case, when you do the decline curve analysis, the idea is to extrapolate present rate data trend to get the EUR. In this example, assuming an abandonment rate of 108,000 standard cubic feet per day, the abandonment time is about 18.7 years, and the EUR is equal 3.61, which is the one we got from ARPS. Okay, now what we're going to do is I'll show you a little bit, let's play with the software. In this case, it's not Sapphire, it's Topaz, and this is the what you have here, the flow rates and the bottom hole pressure. Here we can, if we like, we can show the cumulative 2, and that's the standard, not the standard, but that's the way I presented the data before. So thing here is to analyze this, and then, as I said in the presentation, then make a forecast. So we can have this here, then I'll show you how it's done. First of all, let's go to the map that we have here. And this is where you set your system. This is boundary, could be rectangular, in this case it's circular, but doesn't matter for the case being, because in unconventional reservoir, due that this permeability is almost zero, remember that you need years and years and 100 years to get flow from this part here. What normally is done, you set several of these configurations. You place the configuration in the reservoir. So here you can, I just showed you how Sapphire defined. Here you set your fractures. You can you have a simple configuration. You can have also a complex configuration. Then you can play with according to your what you have actually as a result. This information could come from microseismic. I don't have it here, but you can input it. Okay, so let's go here. Now let's go again to our analysis. What you do now is you, like in pressure transient analysis, you can get you get your pressure and derivative that we see here. And then the thing to do here is you have here a tool, which is this diagnostic tool that can be used to just to help you for doing the analysis. So as you can see here, this is linear flow, and then this is the interference from the other fractures. So what you have to do here is to just to simulate now using a model. Let me show you now this is the Blasingame plot. The thing is, if I now go here and you can have either an analytical solution, as we said before, or in this case we use the numerical solution, which is this one here. If you do that and you start, we're not going to do here because this can take like half an hour, the simulation. If you do that, then you're going to have the solution that is here. Okay, this is you simulate now the log plot, the normalized pressure, and here is your Blasingame plot, which has been simulated, as you can see here. And in addition, you have this decline curve analysis, where that in this case, the one is the hyperbolic, and the way you do the match, let's say that we move this a little bit here, just to show you. You run, you do a regression, then you try to get and then you get a match. So we did this with all the methods that I showed you the results, and here is the way to do it. Go. And here are your parameters. When you fix, you can say the abandonment rate and other features. typical from the client curve analysis. Okay, and this is the linear flow. As I said, this is very important for the monitoring of the fracture. Um, Once you start production, permeability is going to be deteriorated in the fractures, um, and there, because of the stress. And so one thing to do is to monitor that, so you have an idea uh, why is your production declining. So this is all an issue on these unconventional reservoirs. So what you do is to apply this uh, monitoring using this plot here is quite common, and so you can check what is your half distance for the fracture. Okay, and here is just to recreate. This is time zero. You have the whole system with at the pressure, which is 7247. Now let's go ahead for the 3 years, and you're gonna see here how is the pressure and the interference of the fractures uh, goes. And this is okay. It's and well, I think that with this you have an idea how I did the example, and Topaz is the software in this case rather than Sapphire. Okay, so let's go back now here, and this concludes this example. I thank you very much for your attention, and again, and time. And again, you have any questions, if you want the data to check, to just to do the exercise yourself, please let me know, and I'll give it to you.